Hello everyone. Sorry for the late the video I have posted. I think 3 weeks before. So is today I'm going to tell about one paper that was published in previous year in the March. This was my first publication. This paper was published in a good journal like in SOP, Quantum and Continua. So this paper is completely based on means in quantum information computing. Suppose the problem statement is like that. Like suppose you have any kind of robot that now people are using. Like suppose I'm sending one robot to Mars or any planet or to Moon or something. So we have to control that, right? So the basic problem is how can we control that, and what is the efficiency of that? Like there are many cases that it will disconnect to our terrestrial object. Like who is controlling that here? So the paper is based on that, how we can control a space robot or any kind of classical robot by using quantum principles. That's the today's topic. So I want to explain this by using my slides. So I'm sharing my screen. Okay. So now I'm sharing the screen. Okay. So yeah, I have shared the screen. So now I want to present the presentation of this. Okay, let into presentation mode. Yeah. Okay. So I am again welcome to my channel. That I am Biswaranjan Panda from IBM Quantum. So this paper is the reference link is given here, as you can see, and the project, like our research paper name is controlling remote robot, used based on Zidan's quantum computing model. So I have given the link in the description so that you can get access of this research paper. Okay, so move forward. Yeah. So the contents today I want to discuss about. The first is our problem statement that I have given one short introduction to that, and I will tell details. Then introduction to Zidan's quantum computing model that I have used here. Then entanglement measure, which is a part of which is part of our paper. Then Zidan model of quantum computing in details I will explain. Then implementation, how we have implemented. Then I have discovered a lemma there. So I will explain that what lemma tells about. Then the methodology, what method I have used uh, to get results and these kind of things. And the advantages, what are the advantages of our model, and then references. Okay. So yeah. So the problem statement. So the problem statement is the similar type that I have discussed before. Suppose we have a classical robot, which is controlled by quantum computer. Okay. So suppose a given quantum controlled robot that moves in space. We are taking here a space robot in an example, but it will it is for any kind of classical robot. Okay, So which is controlled remotely from a terrestrial station via quantum channel. Okay, so we have to use quantum channel here. So our goal is to control the direction means the movements of robot. Okay, so here we have given the example of direction. Suppose one 2D two-dimensional board is there, and I want to move my robot in four direction, right? One is left, right, backward, forward, like that. Here consider we have considered the remote, 2D and 3D space. So we have given an example of directions, which direction it should go, but still, it is not necessary that it should be the movement. It can be the movements of its hands, like that only. Any kind of. Okay, I think you are clear the problem statement. So going towards, okay. So yeah. So the first thing is our model is based on Zidan's quantum computing. So first of all, we have to get the knowledge of quantum computing. How many types um, we can get reach out to quantum computing. So the first is quantum, quantum circuit model, which is so much popular for that gate based model, that probably X Y Z. So IBM Quantum Composer is there, like it provides us to use free some kind of qubits and simulations. So this is called gate based model. You can go to IBM Quantum Composer and you can get that. Okay, so the means we have to use the gates, like which is analog to classical, analog to no some classical gates you have read before. So it is like that. We have to make the circuit of that, then we'll get our output result. That is called circuit based model. Okay. So the second thing is topological quantum computing model. Okay, so it is quite difficult to get this model. Topological quantum computing people are trying to do that, but still they are not completely successful. But it is one another way that we can get that topological quantum computing. It is related to topological matters, which is in condensed matter. Then they are applying some kinds of rigorous operations, and they are achieving that model, which is quite difficult to get. Okay, so then adiabatic quantum computing model. This is quite popular after the gate-based model. So the thing is, this one adiabatic. Okay, the adiabatic quantum computing model is suppose my adiabatic means a slow process. Okay, so I suppose I have a state psi, and I need to get the final state of that, and I want the solution of the problem. So what I need to do, I have to take the initial Hamiltonian, which is in the ground state of the initial Hamiltonian, and that Hamiltonian will go into the final Hamiltonian, which is also in the ground state. Like it cannot be completely ground state; it is instantaneous ground state of that, the final Hamiltonian. Okay, that will be the solution for that adiabatic quantum optic. Then we come to the another one-way quantum computing model, which is the measurement based model. Like suppose we are taking uh, suppose we are taking entangled qubits. So sorry. So entangled qubit. Then I need to uh okay yeah, so I have to take the entanglement of those qubits, and I have to measure so many times for that, but still it is in progress. It is not a successful model, but yeah, still it is another way to get quantum computing. So, Mohammed Zidan was claimed that he has discovered another kind of novel model which was proposed and based on degree of entanglement, which we call concurrence value. So he claimed that this is another new kind of quantum computation, but still it is based on the based model. Okay, so today we'll discuss detailed. Okay, yeah, so this model was called Giants, no. Okay, so yeah. So there are some applications of Zidan's quantum computing model which we can achieve. I have given the references here, and I will mention in description box also. You can check from that. By these, by using Zidan's quantum computing model, we can make algorithms for like algorithms. Yeah, algorithms for machine learning, deep learning, yeah, these kind of things. Okay, so moving forward. Okay, so now I want to tell about what is entanglement and how we can measure the degree of entanglement. Okay, so as we know before, suppose two states are uh, inseparable. We cannot separate these two states, and if we want to describe one state, and we cannot describe without the another, so it is called these two. If this phenomenon happens, then these two states are called entangled states. This is a correlation in quantum mechanics. So you cannot find this in classical mechanics. So the previous Nobel Prize was on this experimental verification of quantum entanglement, wh- which was gone to Anton Jellinger and Clutcher. Okay, Anton Jellinger, Clutcher, and the another I forgot. Yeah. Okay. Okay. So as we know that two particles are entangled when these are on non-inseparable states. Mathematically, we can denote that by using suppose means using this is the great example of this is one is Bell state, which we can this is the maximally entangled state. The Bell state is. So we'll see further. So the another thing is what is called concurrence value. The concurrence value is the degree of entanglement. See, we can say that these two states are entangled, but how much they are entangled? There should be quantity, right? So if we need the quantity, so the thing which quantifies the quantity of these entangled states, it's called concurrence value, which is degree of entanglement. Okay. So suppose two level system which is defined as psi is equal to E100 plus E201 plus E410 plus E3G10 plus E411. Okay, but if we want to take the degree of measurement, which is called the concurrence value. So the formula is capital C is equal to 2 into E1 into E4 minus E2 into E3. See here, the range is between 0 to 1. So when the concurrence value is 0, that means these two states are not entangled. Sorry, I'm so sorry. I forgot to do that. Okay. So when our entangled value is 0, so it means that these two states are separable. They are not entangled. And when the concurrence value is 1, that means they are maximally entangled, which is the Bell state. I will give one example. Okay, so if I want to take the entangled state, so what I need to do, I'm taking psi as E100 plus E411. Otherwise, you can take E301 plus E210 like that. So as you can see here, these two states are inseparable. You cannot separate these two states. So we can define the measurement concurrence value for that. That is C equal to E1 into E4, which is derived from the previous equation. So we need to verify this. So as we know that our Bell state is uh like 0 0 plus 1 1 divided by root 2, 0 0 minus 1 1 by root 2, like that. Okay, so if I'm calculating the concurrence value for for 0 0 plus 1 1 by root 2, so the coefficients are root 2, right? Here E1 is root 2 and E4 is also root 2. So I'm placing the value of E1 and E4, that is 1 by root 2 into 1 by root 2, that is 1 by 2. Then 2 to cancel, then C equal to 1, which is maximally entangled. As we before, like we know that Bell state is maximally entangled. Okay, this was fine. Go to next slide. Yeah. See. So so now I want to discuss about Zidan's quantum computing model, how we can achieve. The first thing is the model is quantum computing is based on concurrence value, as I have told before. Okay. So the main operations of the proposed model are depicted in figure 1. See what figure 1 tells about. There are psi of t is there, which is the ancilla qubit. Means whatever problem we are taking, according to that qubit will decide, and we'll take the ancilla qubit of that is 0 and h. These are the extra qubit, which is mandatory in Zidan's quantum computing model. Then they have performed certain operations. Then the unitary gate is connecting between the ancilla qubit and our problem qubits. And another two operations are going on. I will explain it in next upcoming slide. Okay. So the another thing which is defined here, like as you have seen in the previous figure, that there are two operations in that. One is one is creating the entanglement between these two qubits G and H. Okay, and then measurement of these two qubits, like we have created the entanglement, and then we will measure the entanglement, which is the degree of entanglement, which is defined as the concurrence value. Okay, so how we can perform this operation by using circuit based model. So we'll see now. Yeah. So MD means Mohammed Zidan given theorem. The theorem 1, how MZ operator can be defined. That operator is MZ. Okay, so theorem 1 tells about, suppose we have a two qubit state, that is psi is equal to e1 0 0 plus e for 1 1, then the quantum circuit shown in figure 3 can be used to measure the degree of entanglement. Okay, so I need to show you the formula for that and the circuit. Yeah, so see, as we know that before, that C is the concurrence value, which can be the another formula, and here I have written this formula in terms of probability. Okay, so how we can achieve that? By using this circuit, we have taken already GH qubit, and again we have to press operate this GH again, and then we have to apply the control not operations. By using simple calculation, then we can achieve this. Okay, so I need to discuss about theorem 3. So suppose we have an qubit, that is G equal to 0, E10 plus E41. Here in E1 and E4, it's a real positive real number, right? So it tells about how we can achieve, how we can get the coefficients of this unknown qubit by using concurrence value. Okay, so this is the formula of that, that G equal to E10 plus E41. Then is defined Z naught by N, 0 plus Z1 by N. This we can get by solving the quadratic equation. This is quite, I think it's complicated, so I have given a lemma of that, how simply we can get, suppose G is defined as alpha 0 plus beta 1, we can get alpha and beta by using that lemma, for a simple calculation. Okay, so here as you can see, Z naught is defined n by 2, 1 minus root 1 minus c square. Here C is the concurrence value. Okay, so we can get Z1 Z naught by using that, and Z naught is n by 2, 1 plus 1 minus c square. Okay, these terms are looking quite complicated, but these are not like that. Okay, so now I want to discuss the lemma of theorem 2. Okay, so what lemma of theorem 2 tells? Yeah, suppose that G qubit is defined as alpha 0 plus beta 1. So how we can get with the alpha? We can get alpha when, see, there are two possibilities here. There are 4 qubits, so there are 4 states also. But if we are dealing with 0 0 0 0, as you've seen, as you have seen before, that we are dealing with 0 0 and 1 1. So there are two possibilities. P0000 is greater than P1111, and another possibility is P0000 is less than P1111, right? So in case of P0000 is greater than P1111, in that case, what will happen? Like alpha can be calculated by 1 plus c root plus 1 minus c root, and beta can be calculated 1 plus c root minus 1 minus c root. And if it is like P0000 is less than P1111, then alpha can be calculated 1 plus 0 minus 1 minus c root, and beta is 1 plus c plus 1 minus c root. Okay. If you want the proof, then I can explain in later videos. If you'll comment here, I will explain the proof. This is a simple calculation, and in our research paper it is mentioned how we have proved this lemma. This is simple calculation. We have taken that the completeness relation conservation of probability, that alpha square plus beta square equal to 1, and C is already defined before. C is equal to 2 into alpha into beta, right? So by using these two equations, I have by using simple algebra like a plus b whole square minus 2ab, by using this formula, I have calculated these two conditions. Now I want to focus here methodology. See, okay. So the methodology is quite simple. The first, we have used the teleportation. We are using teleportation? Because see, I am sending my robot to another planet, space, or any place. So it should be means I have to send two qubit to the robot, then it will be entangled, then I will measure the concurrence value of that, right? This is the procedure, right? So what I need to do, I have to use teleportation. By using teleportation, the qubit will teleport to the robot, and whatever gates I am applying here, I'll show the circuit model of that. How we can implement by our model by using circuit model. So whatever gates I am operating here, it will, like, see, the teleportation protocol is based on entanglement, and we can use entanglement like for infinite distance, right? It doesn't depend on it. It is independent of distance. So this is one advantage of that. That's why we are using teleportation, right? Okay. So another is, as I have told you about Zidan's quantum computing model, we have used. I have discussed completely. If you have any questions or any kind of, you need any new video on this, you need to explain, then then I can explain it here. Okay. Okay. Just a second. There is some problem on that. I'm so sorry about this. Okay. Okay, the lemma is different here. Then I need to show the my yeah. So circuit diagram of that, that is, we have used the unitary gates, whatever we need, like theta. Theta is can be defined as 2 tan inverse beta by alpha, and by using that lemma we can find beta and alpha. So there are two C node gates applied here as according to Zidan's quantum computing model. By using this, we have to take the theta. I'm showing the table of that. Okay. See, the table is like the first, like it is on the 2D space, how it will move. Okay, these are the experimental results of that. You can get in our paper. I'll give the links in my paper in this description box. Okay. So these are the advantages of that. The advantages are quite interesting. You can use it in anywhere, like space robot and water research robot, and in our hotels, any kind of robot. These are the advantages of that. So I don't want to focus on advantages. If you want, then I can bring another video of that. So these are the reference I'll give in our in the description box. You can check that. Okay. If you need anything help and any kind of videos on in quantum computing, I'll free feel free to ask. I'll explain. So on that, bye bye. Have a nice day. Thank you. Stop sharing. Then Okay, bye. Have a nice day.